Hello, my name is Mohammad Rahimi. I'm a data scientist at PubMatic. My friend Hadi Ramazani Dakhal, founder of Prismy, and I formed a team and joined to the Criteo privacy-preserving ML competition. The object of the competition was to predict, click, and sell from noisy aggregated data. We finished the competition in the third place on click prediction and second place on sell prediction. Here I'm going to present our solution in this competition. But before that, I would like to introduce the software that we use for this competition. We use the learner that was developed at Prismy. The learner is able to segment the data and build a classification model. It supports almost all ML algorithms, including XGBoost and LightGBM that we use in this competition. We design a pipeline for data processing and building the models, and the learner help us to speed up our model development time. If you are interested to know more about this software, you can visit the website. It is well documented and you can contact the support team. Model. We have 4 datasets. Train and the test dataset are very similar with 19 features. Feature values are hashed to a signed integer. And as you can see in the picture, the columns are labeled from 0 to 18. Train dataset has 2 additional columns, click and a cell, and we use these 2 binary columns as a target when we train our model. In addition, we have a 2 dataset and 2 aggregated dataset. One of them is a single features, which, as you can see here, we have a feature value and a column ID. And the count tells us how many times we observe this value in this column in whole the data set. Number of clicks tell us how many times we observe the click and how many times we observe the cell in the number of the cell. Very similar, we have a aggregation data for the pairs feature, which tell us how many times we observe the combination of these 2 values for these 2 columns, and how many times we observe the click and how many times we observe the cell. Then normal noise was added to aggregated data. It means that it was added to count number of click and number of cell. And because of this noise, sometimes the value of this number are not logical. For example, we can see the negative value for the number of cell sometimes, and sometimes the cell is larger than the count. Based on some simple analysis and the description of the competition, we know that the train and the test data are actually a subset of the larger data set. This large data set was used for the aggregation, and these 2 samples just for the developing the model. The table here shows the number of the unique value for each column. As you can see, for the features with the low cardinality, the number of the unique value for all the train tests and aggregation are the same. But for some feature with high cardinality like the hash 12, the number of the unique value for the train is much smaller than the test. It means that we have some value in the test that is not available in the train. Therefore, to capture all the pattern the test data, we need to extract or to use the aggregation data, which have more information. In this competition, we spend a lot of time for the feature engineering. Feature engineering is the most important part of this competition, and it will help us to extract information from the old dataset and create one new dataset that is able to use it or consume it by the ML algorithm. We categorize these kind of the feature engineering in 4 categories. The first one is the information that we got from the train dataset. Uh, as I said that we have a same number of the unique value when we have a low cardinality feature. We calculate the click-through rate from the train, and we use it as a one feature because click-through rate from the test doesn't have any noise, so it is more accurate than what we get from the aggregation data. Then we can get some information from the single dataset, like the click-through rate, which is the number of the click by the divided by the count, or the conversion rate, given the click, which is the number of the cell divided by the number of the click. We also calculate the probability of every one value, which is the total count divided by the total, which is the count divided by the total of the count for the one feature. Similar, we calculate some probability from the pair data set. Again, we calculate the click-through rate, conversion rate, and the conversion rate in the click for the pair. Then we try to combine these data and extract more information by combining. One of the most important feature that we created is the P A or B, which is calculated based on this equation. Assume that you have two features with two value A and B, then you can calculate the probability of A. You can assume that click-through rate for value of the A, and you can calculate the probability of the click-through rate for the value of the B from the single data set. Similarly, you can calculate the P A and B from the pair data set. And if you substitute to this equation, you can calculate the probability of observing value A for feature 1 or value B for feature 2. This can be used for all this kind of the probability, like the click-through rate, conversion rate, and conversion rate given the click. The next combination rule that we used to create a new feature was the PCA. The data that we extracted from the single dataset and pair dataset was consumed for the PCA model, and the data was converted into 10 components. And then we used this component as some new features and added to the dataset that we have. So after creating all these features, we map the feature to the train dataset and test dataset, and then develop the one large dataset that I will later tell you how we use this large dataset to develop the one subset of the dataset for the training the model. We also did some pre-processing. The most challenging part in this competition was to eliminate counterintuitive statistics. As I told you, because of some noise that was added to the aggregated data, some value was negative and sometimes the click is larger than the count. So we have some probability with negative value and some probability with larger than 1. So we try to eliminate this problem by using the absolute value if the count is negative, or use the inverse of the probability if we have a probability of the larger than 1. In some case, we try to drop the probability if the count was very small, and then ignore this kind of probability because of the lack of a statistic. The other challenge for the pre-processed missing values. Sometimes we start to using the mean, median, or 0 for impute the missing value. And the last one was duplication. So we observe some duplicate in the train data and we drop them to see if we can get a better score or not. For the training, as I said, we use the learner that was developed at Prismy. We use a different training methods. First, we split the data into the train and the validation. Then we use the cross-validation method, which mostly used for the evaluation of the new features. And finally, we train the entire data set for the final submission. we use two packages, XGBoost and LightGBoost, which both of them are supported by Learner. Prediction of click. For the prediction of the click, we start to generate a two data set from the whole data set that we created after feature engineering. As you can see, for the data set 1, we pick a few number of the features in the data set 2. And the main reason was to generate some diversity in the different data set 1 and the data set 2. And at the end, I will tell you how this helps us to improve the score in this competition. The difference between the only difference between these two datasets is not the number of the feature and the feature. We also have done some different pre-processing for these two datasets and try to improve the scores separately for each dataset. For example, for dataset 1, we only apply some pre-processing to eliminate the counterintuitive statistic when we calculate the P, A, or B. For the evaluation of each data set and understand how this pre-processing should happen or how we have to do the feature selection, we mostly rely on the cross-validation score. And sometimes we check the cross-validation score with the leaderboard. As you can see in the picture in the left-hand side, cross-validation score and the leaderboard score are highly correlated. It means that if we improve and reduce the cross-validation score, we expect to see a leaderboard score also drop. But at some point, we found that it's not possible. It's very difficult to improve the validation score. Then we start to train the model in the entire data set and just evaluate the performance of the model by using the leaderboard score. Here you can see that XGBoost trained in all the data set and as a function of the number of the iteration. So by increasing the iteration, it means with training more and more over fit to the trained data, we can improve the leaderboard score. Finally, we have two data sets. We train each data set with both model XGBoost and LightGBoost. And you can see the leaderboard score for each one. There is no significant difference between XGBoost and LightGBoost. And when we combine these LightGBoost and XGBoost for each data set, we don't see any, significant improvement, slightly improved, but not too much. But when we combine these two combinations from each data set, we see that the leaderboard score is going down. And I think that the main key that we get a good score in the leaderboard for this competition was to generate a two data set and generate some diversity in these two data sets. And then finally, when we combine it, we can get a better score. For the prediction of the cell, we didn't have too much time to create two data sets and generate a data set and ensemble the model to get the best score. Because of this, we only get the most important feature from the data set. And in addition of all the features that I explained in the feature engineering, we add another important feature for the prediction of the cell, which is the click prediction. Click prediction tells us that if the prediction of the click is high, it means there is a high chance that it's lead to the cell. Using this click prediction is a bit tricky. It might give us some leak and get a good score in the training data, but not in the test data. But our evaluation showed that we can use it as one feature based on the score that we get from the leaderboard. Finally, we used this data set and trained the model with only one model XGBoost, and we get this score in the development phase and this score in the final phase. Yeah, that's all. Thank you.